specifically in terms of either procedural standards or unit standards. And the reason we engineers and scientists like to use standards is that it's important that we have these standards so we can compare data across different tests and from different companies, different countries, etc. So we have to follow these standards. Otherwise, it's very difficult to make engineering or manufacturing decisions. So the two most common systems are the inch-pound system or the USCS system that's used in the United States, and then most of the rest of the world uses the international system, which is the scientific standard, and it's based off of 7 base units. Okay, so the base units are shown for your reference here. The base units are for mass, time, length, temperature, current, substance, and luminous intensity. All right. From the base units, we can derive the units for force, energy, power, um, stress, pressure, electrical potential, resistance, charge, capacitance, and inductance. Okay. So um, so these are just shown here. Some of the common units in both the SI system and the USCS system are shown in these tables, and some conversion factors between the two are also given here. All right, you can obviously Google a lot of this information, but it's nice to have it all in one big table. All right, so in addition to the unit standards, there's something called the hierarchy of standards. Okay, so the hierarchy of standards basically explains that there's a single standard that defines what the actual standard is in the world, and then based off of that standards, additional reference standards are made based off of that primary standard. Okay, and then basically from that reference standard, additional standards are made all the way down to like a typical calibration standard. All right, so there's only one primary standard, then there's more from that primary standards, more reference standards are made. All right, then from the reference standard, we have a transfer standard, which then becomes a local standard, so on and so forth. So with each additional um, uh, step or separation from the primary standard, additional errors are uh, put into the system. So um, so based off of so for example, a if you have a primary standard, all right, so the primary standard, for example, is like a fixed thermodynamic point, like the melting temperature at a given pressure of a substance. A transfer standard would be like a specific platinum resistance thermometer that might have a standard uncertainty of 0.005 Kelvin. A working standard would be another platinum resistance thermometer that was calibrated based off of that transfer standard. Might have a uncertainty of 0.05 Kelvin, while a thermocouple is 10 times worse than even the platinum resistance thermometer that was based off of the transfer standard, and that would maybe have an uncertainty of plus or minus half a degree Kelvin. Still pretty good for most things engineers need to do, but you do see that loss in accuracy due to that increased uncertainty in the local standard versus the original primary standard. All right. So so certain testing standards and codes. Um, so different societies often uh, define different standards. So ASME, and then which is mechanical engineers has their own standards for testing different pieces of equipment, and the ASTM or the American Society of Testing Materials has a bunch of different standards for testing different materials. There's also ANSI and there's also ISO. So all these organizations have their own rules and standards for operating different tests to help engineers from around the world be confident and understand the data that they're receiving based off of laboratory tests done.